Estimating electrical load at specific fixture details involves several steps, adhering to the National Electrical Code. Firstly, determine the building type and occupancy. Refer to the building blueprint to understand the space's intended use. Is it residential, commercial, or industrial? Identify the occupants and anticipate their typical electrical requirements. Secondly, estimate the total area and volume. Calculate the total square footage of the building using the blueprints. To determine the volume, multiply the square footage by the average ceiling height. This volume figure may be relevant for certain commercial or industrial load calculations. Thirdly, use NEC-based load factors. The National Electrical Code provides minimum load factors for various building types and occupancies. These factors represent the expected average and maximum electrical load per square foot. For residential buildings, use 3 volt amps per square foot for the average load and 6 volt amps per square foot for the maximum load. For commercial buildings, use 8 volt amps per square foot for the average load and 12 volt amps per square foot for the maximum load. For industrial buildings, use 10 volt amps per square foot for the average load and 15 volt amps per square foot for the maximum load. Fourthly, apply these load factors to the building size. Multiply the total square footage by the appropriate load factor to estimate the average and maximum electrical load. As an example, consider a 2482 square foot residential house. The average load calculation is 2482 square feet multiplied by 3 volt amps per square foot, resulting in 7,446 volt amps. The maximum load calculation is 2482 square feet multiplied by 6 volt amps per square foot, resulting in 14,892 volt amps. Fifthly, adjust for high usage areas. If the building includes areas with known high electrical usage, such as kitchens and bathrooms in a residence, or specific equipment in a commercial space, increase the load estimate accordingly. Refer to the NEC or relevant industry standards for specific guidelines on these adjustments. Sixthly, consider future expansion. Estimates additional load if future expansion or remodeling is planned. This might involve accounting for additional circuits or a larger service capacity. Remember that this method provides a general estimate of the electrical load, and the actual load may vary based on the specific fixtures and equipment installed. Consulting with a qualified electrician for a more accurate load calculation is always advisable. The NEC provides methods to determine the minimum electrical service for dwellings. These methods involve calculating the total connected load and applying demand factors. The general lighting load is calculated at 3 volt amps per square foot, as we previously mentioned. Small appliance branch circuits are required at a minimum of 220 amp circuits for the kitchen and dining areas. These are calculated at 1500 volt amps per circuit. A laundry circuit is required at 1500 volt amps. For appliances, individual appliances rated at 1500 volt amps or more must be calculated at the nameplate rating. For ranges, the NEC provides tables to determine the demand load based on the range's rating. Heating and air conditioning load should be calculated at 100% of the nameplate rating. After calculating the total connected load, demand factors can be applied as permitted by the NEC. For example, a demand factor of 35% can be applied to the neutral conductor for dwelling services. The NEC provides specific requirements for calculating feeder and service loads for dwelling units. These requirements ensure that the electrical system is adequately sized to handle the expected load. Article 220.12 in the NEC covers general lighting loads. This section specifies the minimum volt ampere per square foot requirements for different occupancies. Dwellings are listed at 3 volt amps per square foot. Article 220.14 provides requirements for appliance loads. Small appliance branch circuits and laundry branch circuits are to be calculated at 1500 volt amps each. Article 220.53 covers the calculation of demand factors for ranges and cooking appliances. Tables are provided to determine the demand load based on the rating of the appliance. Article 220.60 1 allows a demand factor to be applied to the neutral conductor size for dwelling services and feeders. This demand factor is typically 70% of the unbalanced load. Article 230 covers service conductors and equipment. This article provides requirements for the size and rating of service conductors, overcurrent protection, and grounding. Article 250 covers grounding and bonding. This article provides requirements for grounding the electrical system to protect against electrical shock and to provide a path for fault current. It's crucial to accurately calculate electrical loads to ensure the safety and reliability of the electrical system. Overloading circuits can lead to overheating, fire hazards, and equipment damage. Proper load calculations help prevent these issues and ensure compliance with the NEC. When estimating electrical loads, consider all potential loads, including lighting, appliances, heating, air conditioning, and any other electrical equipment that will be connected to the system. Use the NEC as a guide, but also consider the specific needs of the building and its occupants. If you are unsure about any aspect of load calculation, consult with a qualified electrician or electrical engineer. They can provide expert guidance and ensure that the electrical system is properly designed and installed. Always prioritize safety when working with electricity. Follow all applicable codes and regulations, and use appropriate safety equipment. Remember that electricity can be dangerous, and it is important to take precautions to protect yourself and others. In addition to the NEC, there may be local codes and regulations that apply to electrical installations. Be sure to check with your local building department to ensure that you are in compliance with all applicable requirements. Accurate load calculations are essential for ensuring the safety and reliability of electrical systems. By following the steps outlined above and consulting with qualified professionals, you can ensure that your electrical system is properly designed and installed. Understanding and adhering to the NEC guidelines for electrical load calculations is paramount for any electrical contractor. The NEC provides a comprehensive framework to ensure the safe and efficient distribution of electricity within a building. Neglecting these guidelines can lead to hazardous situations, including electrical fires, equipment damage, and potential harm to occupants. When starting a new project, the initial step involves a thorough review of the architectural plans. These plans provide crucial information about the building's dimensions, layout, and intended use. Pay close attention to the square footage of each area, as this will be a key factor in determining the general lighting load. The NEC mandates a minimum lighting load of 3 volt amps per square foot for residential occupancies. This value serves as a baseline for estimating the overall lighting requirements of the building. In addition to general lighting, the NEC also requires specific branch circuits for small appliances and laundry areas. These circuits must be rated at 20 amps and are intended to serve the high-demand appliances commonly found in kitchens and laundry rooms. The NEC specifies that each small appliance branch circuit should be calculated at 1500 volt amps. Similarly, the laundry branch circuit should also be calculated at 1500 volt amps. These values ensure that the circuits can handle the expected load from appliances such as toasters, blenders, washing machines, and dryers. When estimating the electrical load for appliances, it's crucial to consider both the nameplate rating of the appliance and any applicable demand factors. The nameplate rating indicates the maximum power consumption of the appliance under normal operating conditions. However, the NEC allows for demand factors to be applied in certain situations, recognizing that not all appliances will be operating at their maximum capacity simultaneously. For example, the NEC provides tables for calculating the demand load for electric ranges and cooking appliances. These tables take into account the size and type of the range and allow for a reduction in the calculated load based on the assumption that all heating elements will not be used at the same time. Heating and air conditioning systems represent a significant portion of the overall electrical load in most buildings. These systems require substantial power to operate, and it's essential to accurately calculate their contribution to the total load. The NEC requires that heating and air conditioning loads be calculated at 100% of their nameplate rating. This means that the full power consumption of the equipment must be included in a load calculation without any demand factors applied. After calculating the individual loads for lighting, appliances, and heating/air conditioning, the next step is to determine the total connected load. This is simply the sum of all the individual loads. However, the total connected load does not necessarily represent the actual load that the electrical system will experience. This is because not all loads will be operating at their maximum capacity simultaneously. To account for this, the NEC allows for demand factors to be applied to the total connected load. Demand factors are multipliers that reduce the calculated load based on the assumption that not all loads will be operating at the same time. The specific demand factors that can be applied depend on the type of occupancy and the nature of the loads. The NEC provides tables and guidelines for determining the appropriate demand factors for various situations. Once the demand factors have been applied, the resulting value is the maximum demand load. This represents the maximum amount of power that the electrical system is expected to draw at any given time. The maximum demand load is a critical factor in determining the size of the service entrance conductors, the overcurrent protection devices, and other components of the electrical system. In addition to the general load calculations outlined above, the NEC also provides specific requirements for calculating the neutral conductor size for dwelling services and feeders. The neutral conductor carries the unbalanced current in a 3-wire or 4-wire electrical system. The NEC allows for a demand factor to be applied to the neutral conductor size, recognizing that the unbalanced current will typically be less than the total phase current. The demand factor for the neutral conductor is typically 70% of the unbalanced load. This means that the neutral conductor can be sized smaller than the phase conductors, resulting in cost savings. However, it's important to carefully calculate the unbalanced load to ensure that the neutral conductor is adequately sized to handle the expected current. Throughout the load calculation process, it's essential to maintain accurate records and documentation. This will not only help ensure the accuracy of the calculations, but also provide a valuable reference for future maintenance and modifications. The documentation should include a detailed breakdown of all the individual loads, the demand factors that were applied, and the resulting maximum demand load. It should also include a description of the assumptions that were made and the sources of information that were used. In addition to the NEC, there may be local codes and regulations that apply to electrical installations. These local codes may have additional requirements or restrictions that must be followed. It's essential to check with the local building department to ensure that the electrical installation complies with all applicable codes and regulations. Accurate electrical load calculations are essential for ensuring the safety and reliability of electrical systems. By following the steps outlined above and consulting with qualified professionals, electrical contractors can ensure that their electrical installations are properly designed and installed. A crucial aspect of electrical load estimation is understanding the difference between connected load and demand load. The connected load is the sum of the ratings of all electrical equipment connected to a circuit or system. The demand load, on the other hand, is the maximum amount of power that the system is expected to draw at any given time. The demand load is always less than or equal to the connected load, because not all equipment will be operating at its maximum capacity simultaneously. Demand factors are used to reduce the connected load to a more realistic estimate of the demand load. These factors are based on historical data and statistical analysis of how different types of loads are used in various occupancies. The NEC provides demand factors for a wide range of loads, including lighting, appliances, heating, air conditioning, and motors. When selecting demand factors, it's important to consider the specific characteristics of the building and its occupants. For example, a building with a large number of computers and electronic equipment will likely have a higher demand load than a building with primarily lighting and general-purpose receptacles. Similarly, a building with a large number of occupants will likely have a higher demand load than a building with few occupants. In addition to demand factors, the NEC also allows for diversity factors to be applied in certain situations. Diversity factors are similar to demand factors, but they are applied to groups of loads rather than individual loads. For example, A diversity factor might be applied to the total load of all the branch circuits in an apartment building, recognizing that not all apartments will be using their electrical systems at the same time. Diversity factors are typically used in large, multi-unit buildings, where the probability of all units operating at their maximum capacity simultaneously is low. When estimating electrical loads, it's important to consider the impact of energy-efficient equipment and practices. Energy-efficient lighting, appliances, and HVAC systems can significantly reduce the overall electrical load of a building. For example, LED lighting consumes significantly less power than traditional incandescent lighting. Similarly, energy-efficient appliances use less power than their older, less efficient counterparts. By incorporating energy-efficient equipment and practices into the design of a building, electrical contractors can reduce the size and cost of the electrical system. They can also help building owners save money on their energy bills and reduce their environmental impact. Another important consideration when estimating electrical loads is the potential for future expansion. Buildings often undergo renovations or additions over time, which can increase the electrical load. It's important to anticipate these future changes and provide adequate capacity in the electrical system to accommodate them. One way to provide for future expansion is to install a larger service entrance than is currently required. This will allow for additional circuits and equipment to be added in the future without having to upgrade the service entrance. Another way to provide for future expansion is to install spare conduits and pull boxes throughout the building. This will make it easier to run new wiring to different areas of the building as needed. In addition to providing for future expansion, it's also important to consider the impact of emerging technologies on electrical loads. New technologies such as electric vehicles, solar panels, and energy storage systems are becoming increasingly popular, and they can have a significant impact on the electrical load of a building. For example, electric vehicle charging stations can draw a significant amount of power, especially if multiple vehicles are being charged simultaneously. Similarly, solar panels can generate electricity during the day, but they can also require backup power from the grid at night or during cloudy days. Energy storage systems can help to balance the load on the electrical system by storing excess energy generated by solar panels and releasing it when it is needed. When estimating electrical loads, it's important to stay up to date on the latest technologies and their potential impact on the electrical system. This will help to ensure that the electrical system is properly designed to meet the current and future needs of the building. Finally, it's important to remember that electrical load estimation is not an exact science. There are many factors that can influence the actual electrical load of a building, and it's impossible to predict them all with certainty. The best approach is to use a combination of historical data, industry standards, and professional judgment to arrive at a reasonable estimate. It's also important to be conservative in your estimates, especially when dealing with critical loads such as emergency lighting and life safety systems. Overestimating the electrical load is always better than underestimating it, as it can help to prevent overloads and ensure the safety and reliability of the electrical system.